Hi everybody, and thank you for coming along to our webinar today. I'm delighted to be joined by Dr. Victoria Beltran. She's a postdoctoral researcher from what was the Axis group, but is now the ACENS group at the University of Antwerp in Belgium. My name is Dr. Mustafa Kansiz. I'm the Director of Product Management and Marketing at Photothermal Spectroscopy Corp. So today's webinar is entitled Submicron Simultaneous IR and Raman for Cultural Heritage. And we, in fact, Victoria, will be going through some new findings in a Van Gogh painting analysis that she conducted. But first, a couple of housekeeping. Throughout the webinar, you can enter questions into the chat box. There's also some marketing material, a brochure that you can download while you go through the webinar. And so we'll answer those questions at the end. And anything we don't get to, we'll get back to you via email as soon as possible. So without really any further ado, I'm going to jump into it, and then about halfway through, I'll hand over to Victoria. So firstly, the outline. I'll take you through some of the limitations, the accepted limitations of FTIR and Raman microscopy. I'll take you through how O-PTIR overcomes all of those limitations. I'll give you a few examples from Mirage, from our other O-PTIR applications before moving over to the core of the webinar, which is, of course, Victoria's part about the Van Gogh painting. I assume most of you are familiar with vibrational spectroscopy, so I won't spend too much time here. Suffice to say that an infrared spectrum has peaks, where each peak is really characteristic of a particular functional group, and the entire spectrum itself thus becomes a fingerprint for that particular material. And I've only labeled 3 functional groups there, but there are a lot more, of course, that you can interpret out. That's really led to vibrational spectroscopy, which of course encompasses IR and Raman, to be used in all facets of analytical spectroscopy. It really is a workhorse instrument. That's not an exaggeration to say. But today, we're focusing on cultural heritage. So starting with some of the IR limitations, and IR can be FTIR, or it can be some of these emerging QCell microscopy techniques. First and foremost, it's limited spatial resolution. As we're dealing with long wavelengths, fundamentally, we can only see so much, and we're limited by those long wavelengths. So practically speaking, that means the spatial resolution with a typical FTIR or QCell microscope is on the order of 10 to 20 microns. Complex sample prep is another key issue. Ideal spectra are recorded in transmission mode, where thin cuts required, 5 to 20 microns. In fact, we'll hear from Victoria later that some of her pieces are even 2 microns thick. So that presents certainly some challenges. Sample contact with the ATR is a way to overcome some of those to some extent, but that brings new challenges. The fact that it requires contact makes targeting difficult. There's risk of cross-contamination. It can damage the crystal. It can even damage the sample, as evidenced by some of these indentation marks. A lot of these IR techniques require cooled detectors with limited hold time, which makes long experiments difficult. There's also, importantly, these dispersive and scatter artifacts. I mentioned before that transmission gives you the best quality spectra. So imagine that's a thin film of a particular polymer. Spectra look very nice. You take the exact same polymer, make it into a bead. Spectra look different. Baseline offsets, shifts, splits. You make it a 10 micron bead, it looks different yet again. 5 micron bead, it looks different yet again. So this really goes to show how dependent the spectra are of particle shape and size and surface roughness. So reflection mode is ideal, especially in the context of cultural heritage, as it's non-destructive. There's no need for thin sections for transmission, which is quite common in cultural heritage. But reflection mode is actually really difficult for infrared microscopy, again, whether it's FTIR or QCell microscopy. It results in poor spectral reproducibility. I actually found a very good example of this from this particular paper. The top there is a smooth polymer surface that looks like PET. But if you roughen that surface up with a bit of sandpaper, the spectra from various points on the same material, so chemistry is the same, but the spectra now are all over the place. So your reproducibility is absolutely shot, and that's because of surface roughness. It can also result in poor SNR, and just generally poor spectral shapes because of some of these dispersive artifacts that I mentioned before, but also competing specular diffuse reflection issues, band saturation, and here's another nice example of that, where a reflection spectrum really doesn't look like the micro ATR spectrum below. You can see maybe a couple of pieces lining up, but most of these have been chopped off. Looks like a combination of maybe some band saturation or diffuse reflection issues creeping in there. Raman, on the other hand, has a lot of other limitations, different limitations. Autofluorescence, especially with colored materials. You can eliminate some of that or mitigate some of that by going to longer wavelengths, but you take a huge hit in sensitivity. And that's on top of an already limited sensitivity. Raman is known to be a fairly low sensitivity technique. It's the fundamental nature of Raman. For imaging, you must do full hyperspectral. You can't do single frequency, which we can with our technique, which I'll show you later. Laser power damage is also a concern because the sensitivity is so poor that you often are pushed to the thresholds of power to get that little bit more sensitivity. But that can be difficult balance to maintain because for dark or colored samples, you risk damaging the sample, and lowering the laser power means lowering your Raman signal to noise. And then there's the issue, of course, that the Raman spectra depend on the excitation to some extent. With certain excitation wavelengths, you can invoke visible resonances, and sometimes the substrate as well can factor into this. So really, to get around all of those issues, one can do O-PTIR, so that's optical photothermal infrared. This technique is really a pump probe optical spectroscopy technique where the pump is a pulse tunable infrared laser, and the probe is a short wavelength visible, typically visible, can be near IR laser as well. It provides for submicron infrared resolution, so it's very much like a Raman in that sense, but it comes with all the richness of infrared spectra. We measure typically in reflection mode, and even though I said reflection mode has a lot of issues, and it does for traditional IR, for O-PTIR and reflection, we generate transmission-like spectra that are completely comparable to existing databases. It's non-contact, and the spatial resolution is constant. So it's not wavelength dependent like it is with regular IR. It's the same across the entire spectrum. So how does this work? Well, we start off with a tunable pulsed QCL, which we focus through a Cassegrain reflective objective, like you have on an FTIR. That's focused to a fairly broad spot because it's a long wavelength laser. At the same time, we collinearly introduce a visible laser, typically a 532, and that's focused much more tightly, down to about half a micron, and that's really the crux of where your majority of your spatial resolution gains are made. And then we monitor the green as we tune our infrared. And when we tune our infrared and hit a particular band, an absorbance, a resonance of a particular vibrational band, that generates a photothermal effect that changes the green reflected light, and we monitor that. So again, we synchronously monitor the green while we tune the IR source, and that generates what is really, essentially, a pure infrared, pure transmission-like spectrum, yet it's been collected in reflection mode. And this can be done in about a second. And taking advantage of the QCL properties, we can tune this to a particular wavelength. So if you want to image only for the carbonyl peak, you can do that. Or if you want to image only for a CH peak, you can do that. In terms of measurement modes, we have basically 3 modes. You can do single point, point and shoot, and get spectra from sort of 500 nanometer spots, and you can automate that process. We can work in array mode where you have minimum step sizes of 50 nanometers for some oversampling. So you can do line arrays, or you can do hyperspectral, sort of, with your more discovery mode type of measurements. We end up with a traditional 3-dimensional data cube. Or you can take advantage, as I said before, of discrete frequency or single frequency imaging, where and we call this sort of targeted mode imaging, where you only image for certain wave numbers. So rather than the entire cube, you may only pull out a few frequencies of interest, and that's much faster, of course. So here I'm going to quickly take you through a comparison of IR, traditional IR and traditional Raman against a few key properties, a few attributes of this system. So spatial resolution is always perhaps number one. There, Raman always wins out, so I'm giving that a green. IR, traditional IR is pretty poor, so I'm giving that a red. Fluorescence, Raman does poorly, IR does very well. There is no fluorescence interference. Sensitivity I mentioned before, that feeds into speed of measurement. Spectrum interpretability and the extensiveness of libraries. There's a lot more, there's about 10 times more IR databases, spectra in those databases than Raman. But Raman works very well in reflection mode, IR doesn't, as I've mentioned. Water vapor is an issue for IR, not for Raman. Solvents, water solvent, sorry, water as a solvent, it's an issue for Raman. Glass is an issue for IR, and I've mentioned that already. So if you look at that, it's not surprising that most labs have one of each instrument, depending on what you're doing, depending on the needs of the experiment. You may use one or the other instrument, or you may even try and measure the same sample and find the same spot in both instruments. But what we do with O-PTIR is basically take the best elements of Raman and IR, and we put those into a single instrument. So literally, we are combining the best of IR and Raman into a single platform. Just to give you an update on some new developments when it comes to pump sources, so your IR sources. So our standard QCL at the moment is a 3-chip device that covers 1800 to 950, so the bulk of your fingerprint. There is an additional laser option that covers the high wave number OH/NH/CH stretching region. But interestingly, there are these new QCL option, new chips that are coming onto the market. So my favorite would be the CH chip that covers 3000 to 2700. And you can combine that with the standard QCL, and then you've got your CH and you've got the bulk of your fingerprint, or the silent region, or you can go for a wide range QCL down to about 800 wave numbers. There's also options for probe, which also doubles as a Raman excitation laser. That's a 532, that's standard. We can do 785 for those samples that are perhaps darker or colored or perhaps fluoresce a lot in the Raman channel. Here's an example of how we compare O-PTIR and existing databases for FTIR transmission. So I'm going to show you some data that was collected, some reference data rather, that was collected as a thin film in transmission mode, probably of about a 10 micron thick section. I'm going to compare that with O-PTIR that's been collected off a thick block in reflection mode. And each one of these spectra of O-PTIR is about a half a micron spot collected in a few seconds. So we see polypropylene, red is FTIR reference, the library reference. Black, we've got the O-PTIR. You can see for polypropylene, it's virtually a perfect match. Same thing polyethylene, same thing with PET, nylon, and polystyrene. So again, just to stress that what we collect in reflection mode is completely comparable to what's been collected in the 30-40 years of history of FTIR transmission libraries. And maybe even, and also, what you may have collected in your own lab. Right, so I talk a lot about spatial resolution. It's important to understand really how that works. So with traditional FTIR and QCLs, spatial resolution is very much a function of wave number, and that's because of this simple equation. And in FTIR land, this wavelength changes a lot, all the way from long wavelengths up this end to short wavelengths, which is why you end up with this curve. And in the fingerprint region, traditional IR gives you spatial resolution that's sort of 10 microns plus on a good day. But for O-PTIR, they get very similar to Raman because it's a fixed probe system. That probe laser is a singular 532 nanometer laser, and that, coupled with the high NA objectives, gives us a theoretical resolution of about 416 nanometers. Right, so that's over a 30x improvement on FTIR. Right. But what's pretty excited people most, I'd say, is the fact that in a world first, we're now combining IR and Raman into a single platform. It's more so a single measurement. So it's really the same spot, same micron resolution at the same time. And how do we do this? That's because we have this pulse tunable QCL that we shine through our objective onto the sample. At the same time, we bring in a collinear pump, a probe beam, where this is where the photothermal magic happens. The reflected green light comes back and is separated by a dichroic filter. So only the Raman shifted light, because we're using a Raman quality laser, there's always the Raman effect happening. Whether we want it or not, whether we even want to use it or not, it's there. So we happen to use it, we collect that light, send it over to the Raman spectrometer for measurement, while simultaneously the unshifted light is detected by the visible detector for infrared signal extraction. So that takes full advantage of the complementarity. It's also confirmatory. IR confirms Raman and vice versa, and it's a singular instrument. Right, so moving over into my applications overview. Conscious of the fact that this is a cultural heritage webinar, I'm not going to focus on many of these other applications, but suffice to say there's lots of cool applications going on. And that's also reflected in the publications that are sort of exponentially rising. I do encourage you to visit our publications website. So I've tried to find examples that have some analogy to cultural heritage, and so we published a paper almost 2 years ago now using infrared and Raman to look at a biodegradable polymer laminate, where on one side we had a PHA film that was laminated to a PLA film, and it was interesting to see what was happening at this interface. So we drew a line array, and we collected spectra at every 100 nanometer intervals, and this is a simultaneous Raman IR measurement. So these data sets were collected simultaneously in the one action. And if I zoom into the O-PTIR, into the IR, the O-PTIR measurements, you can really see how even at 100 nanometer steps, we're actually seeing significant spectral differences across that boundary as we change from crystalline to more amorphous features. And I've just plotted a cross section across this single frequency image, just to highlight that the boundary is fairly diffuse, but the air to polymer boundary is actually pretty sharp at 327 nanometers. This is also pretty, I think, analogous to cultural heritage. This is a forensics application, car paint chips. These are in fact thick sections. These aren't thin, so they've just been sliced off, and we're working off what is really probably a millimeters thick section. And we've got single point spectra collected here, red, green, and blue, collected with the OPO, which is the high wave number laser, and the QCL, which is a fingerprint laser. And you see rich infrared spectra. At the same time, we collected Raman spectra as well, and you can see there's really only one interpretable or useful Raman spectrum there. The red and the green have been swamped by fluorescence. And of course, that hasn't happened on the O-PTIR channel. Right? So that's another example of how, where sometimes Raman just doesn't work because of fluorescence, O-PTIR suffers from zero fluorescence. In fact, we did some imaging on those. We did some single frequency imaging, and you know, there were some sharp interfaces on the left and right side. Yet this middle boundary seemed to demonstrate some mixing was going on. So there was a sort of 2 micron diffuse mixed layer identified in the middle there. Fibers can sometimes be of interest to those in cultural heritage. So I've pulled up this example of polyester fiber that's been coated with some sort of fabric conditioner. And in this case, we're interested to see what's happening along the length of that fiber. So this is a 20 micron fiber, which for O-PTIR is relatively large. And this is a native fiber, so it's free in air. This hasn't been compressed or anything. It's reflection measurements, and these are the spectra along the length. Right, so these are raw spectra, unbaseline corrected. In fact, all of the spectra I'm showing you are raw. And we can see along the length of that, certainly there is some differences in terms of these key additive peaks. But it's important to sort of note that the spectra are independent of particle shape and size, or in this case, fiber diameter. So whether it's a 20 micron or an 800 nanometer fiber, spectra look like interpretable spectra. Right, so in a more traditional setting, these fibers may have been measured with ATR, contact with ATR, or compressed with a diamond compression cell. But this reflection mode is completely non-destructive and non-contact. So here's some sort of performance demonstration proof type of measurements. These are 500 nanometer polystyrene beads, and we've measured one of these individual beads here simultaneously with IR and Raman in about 20 seconds. That's the sort of spectral quality you've gotten from the exact same measurements, or for the same spot with the one measurement. But if we also look at, and these spectra are raw and completely unprocessed. If we look at a cluster of polystyrene beads here, that's about a 4 micron cluster, the spectra look the same. So really, I'm stressing that point because going back to what I said earlier on about the variability that you can get with spectra. With this sort of technique, the spectra are extremely reliable and repeatable. Right? And this is a 20-second measurement. I would be confident that even with a few seconds, you'd have spectra that look almost the same. Okay. This is a real-world plastics, so a microplastic sample. Again, IR and Raman. And I've jokingly mentioned the fact that this was collected by our sales director, so I like to joke about the fact that even a salesman can collect high-quality spectra very quickly and very easily. So if you then put this through a database, in fact, we uniquely work with and partner with Wiley with their know-it-all databases, because whilst we do the simultaneous IR and Raman collection, Wiley with their know-it-all software and equally uniquely do this simultaneous IR and Raman search, where through our software, through the collection software, instrument software, when you've got 2 infrared and Raman spectra, with a single button you can push that into the know-it-all software and then initiate a search, where now the search is expressed in a 2-dimensional plot, where on the bottom axis you've got infrared heat quality index. So this point over here is for a particular spectrum, so that shows you high infrared heat quality index, also a high Raman heat quality index. So that gives us and the user a good example or a good sort of confirmatory analysis. So in this case, the IR has confirmed the Raman match for polycarbonate and vice versa. So really, the takeaways I'd hope you can take out of this, for cultural heritage in particular, is that O-PTIR takes infrared microscopy well beyond what I've termed these accepted limitations. These techniques have been around for decades now and grown accustomed to there being certain limitations. Well, that isn't the case anymore. And now we've combined infrared and Raman into a single platform. So with Submicron, you see a lot more detail. With this non-contact reflection mode, you can work in that easy mode without any ATR, without any cross-contamination. There are no dispersive scatter artifacts, so you can see that the spectra are very consistent, doesn't matter the size or the roughness. There's little to no preparation, so there's no need for thin sections anymore, which can be, I know, very challenging. You can work off thick sections, or even rough material. It can be work off a piece of metal or a piece of glass or some other rough surface. And there are now new QCL options coming out onto the market, especially the CH. I think has opened up a lot of new experimental possibilities. I'm going to finish up by again reminding you of IR+Raman, giving us the same spot, same time, same submicron resolution measurements. And with that, I'm going to hand over to Victoria. Thank you. Victoria, take it away.
So, many thanks for this interesting presentation to the technique. I'm going to talk now about the application of O-PTIR spectroscopy to the analysis of historical paintings. Specifically, I'm going to talk about the painting from Bangkok entitled L'Arlésienne, of Madame Ginoux. We did this study together with my colleagues from the Essence Lab from the University of Antwerp in Belgium, our colleagues from the Royal Model Museum in Netherlands, and the Celestine Coton in France. This is a painting entitled L'Arlésienne, Portrait of Madame Ginoux. It was painted by Van Gogh in 1890. It is a small painting on canvas. It's around 90 per 70 centimeters, so it's quite small, and I display it in the Royal Model Museum in Netherlands. It can be seen, the painting displays a woman with a pink background. we could see that this pink background has faded compared to the original when it was originally painted. We know that because the areas that are covered by the frame shows brighter pink tone, the areas that are exposed to the light. So knowing this, it was very interesting to understand which pigment was used to produce this pink color, because then it would be possible to think which are the most suitable strategies for preservation of the painting and to mitigate or avoid, if possible, the degradation of this background. So to do this, to understand which is the pigment from this background, we took samples. The sample extraction is very limited because we are talking about a painting of Van Gogh, and then the painting is very valuable, so it was not possible to have like a big sample. The only sample we could extract was a small fragment of 200 by 200 by 25 microns. We can see it here. It covers from the layer. We can see here the particles in the image from the left, and there are also the layers until the canvas. We can see also the canvas fibers. So it's the word stratigraphy of the painting. This is more fragment we embed in synthetic resin, and we put fill sections microns. We did that because some of the techniques that we use for the study required to have an transmission, and this was the thickness that was needed to make these transmission measurements. So in this section, we can see which are the size of the painting fragment. It's actually 75 microns by 20 microns, so it's really small. Looking closer to the section we could see that actually there are different layers in the fragment. First of all, we have the layer which is consisting in the canvas, when the canvas itself, with the fibers and some of the glue, probably used as a sizing agent. Then we have the painting fragment that consists basically in two layers. The ground layer, which is whitish, and it's about 10 microns, and then the painting layer, which includes this kind of particles, and it's again 10 microns. So this thickness of the painting layers is unusually thin. It's very thin. For normally you can find much thicker layers than this. In this top layer, you can see these thin particles I was mentioning. They are quite small. They are around 2 micron thickness diameter. 2 micron diameter. And these are the bigger ones because we can see that there are areas where the particles cannot even be distinguished by the microscopic image. So, having these samples already prepared, we went for the first step of our study, which consists in analysis of the stratigraphy of the painting. This stratigraphy was knowing the component of the stratigraphy was needed because knowing the metrics of the painting allowed us to discriminate which is the composition of the pink particles. So to make this analysis of the stratigraphy, we did first a multi-technical study using micro-FTIR, coupled synchrotron radiation, and O-PTIR. We use synchrotron IR because actually it's one of the techniques that we use that has higher resolution. It is much higher than the conventional STIR and the benchtop one, because with benchtop FTIR we can reach 30 by 30 microns size, while with the synchrotron one we can reach 6 by 6. We are talking about the whole range of mid-IR. Besides, synchrotron IR has a high signal-to-noise ratio and high spectral quality. So it's possible to see even the very subtle features of the spectra and have a very accurate interpretation. Then we compare this measurement with O-PTIR because O-PTIR provides a higher resolution than synchrotron IR, we could have analyzed a spot of 450 nanometers by 450. And also something which is very important for us in this type of samples is that the analysis doesn't need to, that the sample doesn't need to be in contact with anything during the measurement. This is important for us because the samples from cultural heritage and also from historical paintings are very brittle, then they tend to break very easily and fragments are easily detached. So with techniques, for instance, AFM, IR, also known as non-IR, we can also reach very high resolution, but it requires a contact with the sample. AFM IR is consists in the coupling the AFM with the IR spectroscopy, and AFM means to have a cantilever, and the cantilever needs to be touching the sample. And this subtle touch we have seen before in other samples that it may cause some damage to the sample. So that's why we prepared something that would avoid the contact with the sample. So these are the measurements we obtained with synchrotron FTIR. This is the, here we can see the area that we analyzed. It's quite small, but it contains the whole painting sample. And we could see the main components of the sample. We could see epoxy, we could see also protein and cellulose. Epoxy is the resin that was used to prepare the sample, to embed it. And then protein and cellulose are probably related to the canvas. Cellulose are related probably to the fibers used to prepare the canvas, and protein is probably related to the animal glue, or sometimes some sort of glue used as a sizing agent for the canvas. And then we can see also lead white, calcium carbonate, and drying oil, which are related to the composition of the painting itself. Drying oil is normally the binding media, which is, since it is an oil painting, we expected something like that. And then lead white and calcium carbonate are two white pigments widely used in oil painting. So here we have the result of O-PTIR. The O-PTIR was applied only in this region marked in orange in the image. And from this small region, we can already see all the compounds that we are seeing also in the FTIR measurement. We can see the epoxy resin, which are surrounding the sample. Then we can see the protein linked to the canvas and the two pigments, lead white and calcium carbonate, as well as the drying oil. Interestingly, O-PTIR measurements didn't provide only the compounds, but also we could see the distribution of these compounds across the painting layers. Specifically for lead white and calcium carbonate, that in the synchrotron IR, we can just see that they are belonging to the painting layers. In the O-PTIR, we can see how they are distributed. We can see that lead white is mostly in the top part of the layers, while calcium carbonate is mostly in the bottom and in the middle. And then drying oil is spread all over the layers. So these O-PTIR measurements provide additional information about the compounds. So from these first results, we could see that indeed, compared to synchrotron FTIR, O-PTIR has a higher spatial resolution. And this provided additional information which was valuable to understand the composition of the painting and how it was made. I want to show also some spectra we collected with both techniques, with synchrotron IR and O-PTIR. And from one side, with synchrotron IR, we could see that the spectra we obtain are very good quality, very good spectral quality. The noise is very low, and the baseline is flat. There are no spectral artifacts. This is a technique which is well known for this. So these are the results that we were expecting. But from the side of the O-PTIR, we could see that the spectra we obtained actually are also very good. The signal to noise ratio is quite low. It's true that in the lower wavelengths, there are also a bit of noise compared to the synchrotron IR, but still the signal is very under this is very good, and the bands are all of them distinguishable. Also, there are no spectral artifacts, and the design is very straight. The spectra from O-PTIR can be easily compared to other spectra collected in transmission FTIR. So this allows to interpret the data using the databases previously collected for transmission FTIR, which helps to understand the results. And something else I wanted to remark is that the relative intensities are also very comparable to synchrotron FTIR, and this is also helping to interpret the data. I would like to give specifically detail on this band at 1510. This band is related to the epoxy resin, and as we can see in the results from the synchrotron FTIR, we can see this band in all the spectra collected, while in O-PTIR we can just see them. We can see the band only in the epoxy areas. And the explanation for this is that because of the spot size analyzed in synchrotron IR is bigger, it was difficult to just analyze areas that were exactly inside of the sample. It was easy to that the analyzed areas included small regions of the embedding resin, or regions that are close to the edge of the sample that where the embedding resin has infiltrated. So as a result, we obtained that this band related to the epoxy resin, which was overlapping with the other results, and having more bands in the spectra, having more overlapped bands, difficult interpretation, and that doesn't allow to have so accurate results. However, in O-PTIR, this band is not present in all the spectra we collected, and this is because the spot size was way smaller, and we could select easily areas which are only inside the sample. So we could observe the spectra of, for instance, the linseed oil, but drying oil with a pigment without the interference of the epoxy resin. Having less overlapped spectra, it helps to interpretation. So this was a very interesting point for us. So as a conclusion from here, we could say that synchrotron FTIR, O-PTIR compared to synchrotron FTIR, provides a high spectral resolution, a high signal-to-noise ratio, and high spectral quality. And it's true the only weak point we could find was regarding the length of the measurements, because for sure, since O-PTIR has a high resolution, each area has more points to be analyzed. So it takes longer to analyze the same size of the area by synchrotron FTIR than O-PTIR. But still, the time scale was good enough, and we could analyze all the components needed for the analysis easily with O-PTIR. So it was not something that was difficult at all our measurement. Having characterized the matrix of the painting, the second stage was to characterize the pink particles. So for this, we started by conventional techniques, by synchrotron IR, Raman spectroscopy, and scanning electron microscopy, SEMI-DX, to have a first approach to the composition of these pigment particles. On the synchrotron FTIR, we could see that, as shown before, that the spatial resolution is too low. The particles are very small, are 2 microns, more or less, diameter, the bigger ones. And since the spot size of this technique was 6 by 6 microns, we were not able to find any marker from the spectra that could be related to a pink particle or a pink pigment. So this technique was discarded for the characterization of the pink particles. For this reason, we went for Raman spectroscopy. For Raman spectroscopy, the equipment we are using is the 785 nanometers laser. We could see, we could obtain analyze a spot of around 2 microns diameter. So we took one of these big particles in the sample, and we obtained different spots across the particle. And we could see that in the spectra we obtained, well, indeed, we can see the bands of the lead white, that we know that they are related to the matrix, since we did the study I mentioned before. But there are also some areas, some peaks around 1430, 1307, and 1249 that are located in the region where there are bands also from geranium flakes. Geranium flake is also a pink pigment, pink red pigment used by Van Gogh in the same period of the painting. So it would make sense to have it in the sample. However, these signals are quite small. The signals are broad. We consider that this is because the technique has also not enough spatial resolution, and the pigment particles are quite small. So, although these bands and these signals agree with the geranium flake references, they don't allow to discriminate unambiguously the presence of this pigment. So we discarded this technique as a definitive technique to understand which was the pigment composition. And finally, we went for semi-DX. In the semi-DX results, we could see that actually there was presence of bromine. There was presence of bromine specifically in the areas that were painted with these pink particles. No? But and this bromine actually was not present in the areas, or either in the iris ground layer, which is white, without particles, and also there is not present in the background. So it seems that the presence of bromine is correlated to the pink regions, and the presence of bromine is also linked to the presence of geranium flakes, since this molecule has bromine bonds in the xanthine group. So it would agree. These results would agree with the presence of geranium flakes in the painting. But still, since we don't have molecular information, we consider it's not enough to discriminate the presence of this pigment, again, unambiguously. It agrees, but it's not enough. So with these first results, we went for O-PTIR measurements. With O-PTIR measurements, we analyzed this small region of the sample, and we took different measurements in pink regions, and we could obtain, compared to the other techniques, a clear result. We could see that the O-PTIR has also the presence of other bands linked to lead white and drying oil, and this is normal because we saw that in the matrix in the previous measurements. But also there are other bands which are clearly related to the presence of geranium flake, that we can see here also in the geranium flake reference. So we consider that with these measurements, having all the bands from geranium flake reference, we can finally conclude that this is the pigment that is used to give this pink color to the background. So this allows us to give a conclusive results of the composition, being then the only technique that was able to characterize successfully this material. So as a conclusion, from all this study, we could say that O-PTIR provided accurate information regarding not only the presence of compounds in the matrix, but also how they are distributed across the layer. O-PTIR provided a good spectral quality, and with good signal-to-noise ratio spectra, with low noise, and with spectra with relative intensities comparable to FTIR transmission. So very promising results. And besides, O-PTIR was the only technique that was able to successfully characterize the pink particles. And this was interesting because we couldn't do that with other conventional techniques, even though we tried a multi-technique approach. This synchrotron FTIR, Raman spectroscopy, and semi-DX. So this indeed shows the potential of this technique in this field. Finally, I want to acknowledge my colleagues who also participate in this research from University of Antwerp, from Synchrotron Soleil, and also from Royal Memorial Museum. And I want to acknowledge as well the funding support from University of Antwerp, the FWO Agency, and the Soleil Synchrotron. So many thanks for your attention. If you have any question, I would try to answer you.
Thank you, Victoria, for that really brilliant talk. You know, as a product manager for this product line, it brings me great joy to see that you know, it was only through O-PTIR that you were able to identify those layers that those other established techniques could not. So as you've been talking, I've been watching some of the questions come in. There's quite a few. I'm going to send some of them your way. I'll start with this first one here. Is there any radiation damage from the laser for the O-PTIR analysis? Victoria?
Well, indeed, we were a bit concerned by this thing because, as I said, geranium lakes is a pigment which is damaged by the light exposure. So it was this was an option that we were considering. However, we tried to repeat the measurements of O-PTIR in the particle for repeating the same point, exactly the same area, different times. We tried till 20 times, and we couldn't see a variation in the spectra obtained. So for this material itself, the radiation damage was not a concern. It was not a problem. It didn't affect the sample composition. However, it is possible that this could happen in other type of materials. So perhaps more in-depth, study more in depth about this subject should be done, and sure it should be optimized. Maybe other type of mitigation strategies in case that radiation damage is found in other types of materials.
Thank you for that. Actually, I've got a follow-up question, or maybe even a comment to that. So, I assume when you were using this, you were using the special low-power detector, the APD. Is that what you used?
Sorry, I don't know which detector.
Yeah, because I think given that what your comments triggered me there, you said that this is a pigment, so they're usually very sensitive to bright light, and that's you know, one of the features of this technique is you have two detectors to choose one. You have a sort of a high power, high light level detector, which is our silicon standard photodiode, and then there's the extremely low light level detector, the APD, which operates on kind of tens of microwatts of power. So typically things that you really have difficulty getting a good Raman signal from, you can get excellent O-PTIR data even with only tens of microwatts of power. Okay, the next question, actually this one's probably more for me. How does O-PTIR not suffer from fluorescence if you use a Raman laser? And this is actually a pretty common question. It's kind of an obvious question. We talk about how we use a Raman grade laser to measure the IR signal, but on the one hand, those sorts of lasers can generate a lot of fluorescence. And sure, even on our fluorescence channel, you still can get fluorescence if it's there in the sample. But even if you have the world's most fluorescing sample, for the O-PTIR measurements, it simply will not affect the O-PTIR channel. And that's because the O-PTIR signal is modulated from the modulation or the pulsing of the QCL. And we use a lock-in amplifier to extract out only the modulated signal. And it's only the infrared signal that will be modulated. The fluorescent signal will be constant. So that's a very efficient way to extract out, or to rather filter out, any fluorescence interferences. And that's how we can avoid fluorescence entirely in the O-PTIR. Victoria, this question I'm going to throw to you. They say a 2-micron thin section would be difficult to cut. Can you use thicker sections?
Indeed, we used 2-micron thin sections because we wanted to couple, as I said, to synchrotron FTIR, in transmission. We use transmission as synchronous FTIR because this is the mode that we can obtain higher signal-to-noise ratio. But this was not a requirement for O-PTIR measurements. Indeed, we have done more experiments in other type of cultural heritage objects, including small pieces of degraded glass or degraded metal, and there was no need for such a thin section. We just apply it in the top of the surface of this tiny object, and we got very good results as well.
Actually, that's a really good point, because a lot of people go to a lot of trouble to prepare the sample appropriately for FTIR measurements, and like you say, transmission gives you the best quality data typically, but for transmission you need very thin sections, which depending on the sample can be very difficult. And it's one of the strengths of O-PTIR is that it doesn't matter the thickness of the sample, whether it's 2 microns, whether it's 2 millimeters or 10 millimeters, smooth or rough, the spectra you get back in reflection mode look like FTIR transmission mode data, which means they are fully compatible with all of the libraries that have been used for 30, 40 years. Next question. Yes, what is the depth of sample, depth of sampling? So that's probably one I'll take. The depth of sampling, of course, it depends. It depends on the nature of the sample, how absorbing the sample is, which infrared wavelength you're at. But as a rule of thumb, as an approximation, we typically say it's kind of a few microns to maybe several microns depth-wise is what you'll be measuring from. The next question, spectral ranges, are other spectral ranges available? I'll answer that one as well. I think, Victoria, so you used probably one of the earlier QCLs that was on that system in Soleil. I know they have since been upgraded to have a new QCL which has a wider spectral range, and really exciting, they also have access now to the CH stretching region, which is pretty novel for QCL. So the standard QCLs now do about 1,800 to about 950. They can go down to about 800. But the one that Soleil has, and I think they're unique at the moment, fortunately I think this is after your results were collected, will also now have the CH stretching region, so from about 3,000 to 700. The next question, Victoria, I'm going to throw your way. Does this, kind of similar to the other question really, does a sample need to have a flat surface in order to be analyzed by O-PTIR?
Well, from our experience, we saw that, of course, the sample should be a bit flat to have some signal, but it doesn't need to be totally flat. For instance, like other techniques such as ASMIR. It has to be, we have applied, for instance, as I was mentioning, in small objects which have like a rough surface, and we could obtain very good data from that. So something flat, more or less flat, is needed, but this requirement is not as big as in other techniques.
Okay, thank you. This next question I'll take. This one I think came in when I was talking about detectors. What detectors are used, and do you need liquid nitrogen cooling? So that's another common question I get. So in traditional FTIR instruments, especially the microscopy instruments, and probably the microscope you used as well on the synchrotron, use liquid nitrogen cooled infrared detectors, and you need that liquid nitrogen cooling to increase the sensitivity for infrared measurements. But the key to really remember with this sort of system is that once the sample is excited by the infrared laser, everything else in the system is done in the optical region. So all of the probe beam is measured with a visible detector. So that is a room temperature silicon visible detector. Even that high sensitivity, low light detector I mentioned to you, Victoria, is the APD, and that's also a room temperature detector. So that's really advantageous because you really don't want to be filling up liquid nitrogen. If you're doing a long measurement, you don't want to have to come in late at night and top up the liquid nitrogen or risk the experiment failing. Some more questions. This one I'll throw to you as well, Victoria. One of the criticisms of cross sections is getting smearing between the layers. Can you comment on this, and did you see any evidence of this?
In this case, from this sample, we see that. It's true that another type of samples, it could be a problem. But again, since this technique doesn't involve any contact between the equipment and the sample itself, this was not a big concern for us. For instance, in other techniques that involve a contact, as I was mentioning, AFMIR, we could see that there was particles that were dragged from one layer to the other. But in this case, since the sample, of course, was prepared and in a suitable way, and there was no contact, we could not observe any effect like that.
All right, we're getting near the end of these questions. There's quite a lot coming in. That's always a good sign. Can you use different probe lasers, and how will the results change? So I'll take that one. So our standard probe laser is a 532. Of course, that measures the infrared. Also is the Raman excitation laser, and that's a good general laser because it's quite strong, especially for the Raman, and it also provides good spatial resolution. We do have the option for a 785 probe beam. That's particularly useful for samples that are likely to fluoresce on the Raman channel with the 532. Sometimes a green laser can burn the sample, especially if it's dark or if it's reddish in color, which is why sometimes the 785 can be advantageous. And yeah, there are sort of two standard lasers. Of course, the technique is theoretically compatible with a wide range from really UV to near IR. So if there's any particular interests, you can always reach out to me individually. And you know what's the next one here? Yes, this is really the last one. How does the sensitivity compare to Raman? Well, I'll get your take as well, Victoria, in a second. But in my experience, Raman is known to be quite a low sensitivity technique, sort of fundamentally how it works. Whereas infrared is orders of magnitude fundamentally a lot more sensitive compared to Raman, and certainly that's in our experience. Even when we're doing infrared simultaneous in Raman, typically we have to scan longer on the Raman so the Raman can catch up to the infrared. So that's one of the many advantages of infrared, and in particular O-PTIR, is that you can take advantage of the fundamentally more sensitive nature of infrared. Victoria, do you have any comments about Raman versus IR sensitivity in your experience?
Well, I have also this, I agree with you that IR is more sensitive than Raman, and we should say as well that Raman has, well, in this case, it's proved that the Raman can cause damage to the samples. We have seen that in many types of materials. So, yeah, in this case, for us, it's not just about a matter of sensitivity, it's also a matter that the Raman can damage the samples, and having samples from cultural heritage, the possible damage of the sample is a big deal.
Okay, well, thank you. And with that, let's bring this webinar to a close. So, Victoria, thank you again for taking the time out of your busy schedule. I was really excited when I saw your paper come out, and I thought, well, we have to get you onto our webinar series. So, thank you for accepting my request. I also want to thank the audience for their time. A lot of this recording will be available on our website within a couple of days, but we'll send an email out to everybody anyway. So with that on-demand webinar, so if you want to share that with any of your colleagues and friends, you can do so. And that's really the end. So everybody, wish you a good day. Thank you. Bye-bye. Bye-bye.
Thank you.